Hello and welcome to Powerbench. I'm going to be testing some powerbanks, starting with this one. It's a freebie, it came from an event and it was given to me by a company at that event. I've covered their logo because it doesn't seem fair. I've had this a few years. It's not very good. Every time you use it, it seems to be out of charge. I've no idea what the capacity is. I don't use it much, to be honest, but it seemed like a good place to start with these. It's a bit of a practice run. So first of all, I've weighed it. It's 66 grams, which is about 2.5 ounces. It's quite portable, pocket-sized. It's not very big. There you go. So 9 centimeters long, and about 2.5 wide. If you can see that. So it's I suspect it contains a single 18650 cell, but I haven't taken it apart. I will be taking this one apart on the video because I don't really want it anymore. Normally when I test these I won't be taking them apart because I'd rather keep the power banks or give them away, which I'd like to do for some patrons as a kind of incentive. So first things first, we are going to test its the amount of power it can output. So normally USB is 500 milliamps at 5 volts. This has been pushed to 1 amp and 2.1 amps for various chargers. So smartphones used to be around 1 amp. Some of them now draw more. But for standard USB, 1 amp or 2.1 amps is normal for a charger. I don't know what this will do. You can see it's got a standard USB socket, and then there's a micro USB socket which is used for charging. So the input on the bottom, output on the top. It comes with a little cable which I will also test. But in order to test the capacity, I'm going to use this little USB load. Basically, it takes the power and wastes it as heat, which is why it's got a heatsink and a fan on it. There's a little display so you can see how much power it's drawing and the voltage that the power bank is outputting. 2 adjustment knobs so you can adjust how much power it draws, how much current it draws, strictly speaking. So if I plug it in, this thing boots. You can see it's drawing 5. So the power bank is supplying no amps at the moment, no current, a tiny amount just to run the display at 5.2 volts. And as we turn this up, we'll see what the behaviour of the power bank is. So the voltage drops ever so slightly as the power goes up, but nothing too drastic, which is good. It's consistently above 5 volts, which is what we're looking for. So half an amp, this is standard USB, is doing that just fine. So if we turn the power up a little bit further, we go to 1 amp. Oh, gone a little too far. There we go. So it seems to be doing that just fine. 5.2 volts or 1 amp. Will it go to 2 amps? I'll turn this up gently because the display doesn't update very often and it's powered off. So just over 1 amp, so that's good to know. This outputs 1 amp really. I assume. I mean, it's I think I've had this 4 years probably, certainly 3. So it's not especially current, and it was free, so can't really complain. So the next thing to do will be to test the cable that came with it, and that is this. It's white, it's reasonably flexible, it feels quite thick, so I don't know how good a quality it is, but we'll find out. This cable is 30 centimeters long, just over, so it's about 1 foot long, which is fine. That's about all you need for a little portable power bank. So this, again, this little USB load has on its back a bunch of other sockets, so you can test Lightning, micro USB, USB-C, and mini USB. Not as many devices using that these days. So what I'm going to do is, first of all, so this is the cable. You can use it either way around to charge or to supply power to a phone. If I plug this into the my USB supply on the desk. You can see when you plug it in, I get the socket the right around. There's a little red charging light comes on while it's charging, and that does go off when it's finished charging, so it's good to know. So again, if I plug this in, what I'm actually going to do, I have this little meter, this little USB meter. It's got a really nice display on it, as I'll show you in a second if I plug it in. So it shows up really well in the videos. And then into that I'm going to connect the little white cable that came with it. So this is showing ever so slight current draw because the meter is powered by the device, so it does use a tiny amount of power to light up the display, which is mildly irritating, but the meter I'll be using later to do the actual measurement doesn't, that has its own independent power. So I will plug this into the back of this, like so. And what we see is they both report more or less the same voltage at 0 amps, pretty much. Again, tiny amount of draw because this is now lighting up two little displays, but that's to be expected. So as we turn up the voltage, as we turn up the current, sorry, I'm expecting there to be some voltage loss because all cables do lose a little bit. This one will be no exception. Higher quality the cable generally, the more copper it contains, and the more copper it contains, the less voltage you lose across the length of the cable. Now, voltage loss basically means heat wasted, so you're losing power as heat, and the more of that you get, obviously the slower your device charges, and the more of your power bank power is being wasted. So if we turn this up to 1 amp, which is what that power supply is capable of generating, power bank is capable of supplying, slightly under, use the fine adjustment dial. Okay, so 1 amp exactly. You can see the power bank at this point, we're seeing 5.15 volts on this meter, and then the other side of the cable, 4.35 volts, 4.36, which is not very good. That means we're losing 0.7 volts across the length of the little white cable, which is effectively about 10% of the power being supplied. So that's not very good at all. In order to show you a good cable, so at 1 amp, 4.35 volts, if I swap this for a good cable, this is a brand new Anchor branded cable that's designed for high power deliveries. It's got the power conductors are large copper ones, and using the same method, you can see 4.97 volts, so this one's 0.2 of a volt, less than 0.2 of a volt, so it's about a quarter of the power loss, and this cable is 3 feet long instead of 1 feet long, so it's 3 times longer and has significantly less power loss over it. So cheap cables are a false economy. Not that these are particularly expensive. I can't remember how much I paid. I'll try and do a video overlay for how much this cable cost me. But this one is garbage. It's clearly all of the nice feeling is plastic insulation. The actual copper conductors for power are tiny, which is a shame, but it was free, so I can't really complain. The next step is going to be to recharge this, which I will do now, and then we'll do a capacity test. So, as you can see, the charging light is out. The meter reports it's not drawing any current, which is good. So, this is fully charged. Now, in order to test this, I've got the oscilloscope hooked up and turned on. Let's angle this slightly better. So this will be logging data to the computer every 30 seconds, so we can plot the current and the voltage over however long it takes this to run out. Voltage is from this probe here. Current is measured by the voltage drop over this shunt resistor. A slightly complicated setup. Let me separate these out slightly. I'll be using this meter to do the actual measurement. It has this internal power supply, so it doesn't rely on the power bank for its own power. The screen's not as good, which is why I'm not using it in other parts of the video. So what I'll do is, in a second, I will plug in the load. Now I've got an extra thing plugged into the load at the moment, which has got some USB Christmas lights on, because it makes it obvious when the power goes off. So I could do with a bit more screen here, but let's move this back slightly. So the setup is effectively, let me get this out of the way, remove the cable, so this is not going to be a factor. So we plug the power bank into the meter. The meter will read all of the power delivered, regardless of, so it'll take into account power losses from the shunt resistor and cabling. We'll be able to see the screen on this, but again, we're not going to use these measurements for the important accurate ones. Christmas lights, I'll try and get those in frame so we can see when it goes off. And I'll speed up the video so you don't have to sit and watch it for an hour or however long it takes. So let's plug the load in here. What we'll do is, this is down to 0 at the moment, we'll increase that to, there we go, there's a light in shot. We'll increase this to 1 amp, which is a reasonable draw. I'm going to prop this meter up so everything's zeroed on it. I'm going to prop this up on the multimeter so that it's a little bit more visible, and then we will plug it in. Set the current on the USB load, and then leave it for however long it takes. So lights are on. The meter is counting. Angle that up slightly, you can probably see, make out numbers on it. Let's increase this to 1 amp. I apologise for the noise of the oscilloscope. Right, there we go. 1 amp. This will vary slightly because it's not temperature adjusted, so as it gets warm it may increase slightly, but that's close enough. So you can see on the oscilloscope the voltage has remained constant, that's the blue line at the top. As I've cranked up the, there we go, it's just reset, so it resets the count every time it takes a measurement. But as we vary the current on the load, you can see the yellow line increasing, so those are being logged. We've got numbers coming up on this meter here. It's currently showing just over an amp, 15 milliamp hours so far, and we've got USB Christmas lights are on. So what I'm going to do is turn off the fill light and let it record. So this is exciting. It looks like it's struggling to supply power. You can see that the very faint light actually on the USB power bank is flashing at the same rate that it's failing to deliver power. The meter is showing it dropping to 3 volts intermittently, which is bad. Obviously the oscilloscope is showing the same behaviour. Power drops off significantly. and it's enough to make the lights go dim. So I've no idea how well the little load is going to cope with this, but it seems to be doing okay so far. Obviously the meter carries its own independent power, which is why I'm using this one. So basically you've just got to wait for it to die, but it's only showing 221 milliamp hours used so far, which is not a huge amount. I'll take a screenshot of the oscilloscope so you can see the what that looks like. I'll put that in the video, and we'll wait and see what happens. I think in order to give it a fighting chance, I'm going to lower the current slightly. Given I don't know the spec of this thing, I'm going to drop it to 500 milliamps. You can see on the oscilloscope that that's dropped off nicely. That does seem to have improved it, so whether it'll keep behaving or whether it will start to show the same behaviour again as the battery loses more capacity, more power, we'll see. So I don't know if you can hear that. Voltage is dropping steadily, and there's quite a high-pitched noise coming from the power bank, which appears to have gone quiet now. So I think it's about dead. You can see from the oscilloscope the voltage dropping quite steadily, 3.1 volts. The lights are getting dimmer, they're not gone out yet, but 2.9 volts. I think any second now the load is going to shut off. Two and a half volts. Two volts. Still going. I mean, this is well out of spec for USB now. Slightly alarming that it doesn't just cut off. More reputable power banks just kill the power when they get too empty. I'm a little bit concerned that this is going to keep going. So I think I'm going to stop it. It's under 2 volts now, which is way below. Even the lights have gone out now. So I'm going to unplug the load. And so the final reading at this point is 1162 milliamp, or 1.162 ampere hours, according to this meter. Which, see if I can light it up. It's not a very good display, this one. 1.162 ampere hours at 5 volts, which would be 1570 3.7 volts. So I would guess there's going to be some losses, but I guess this is probably an 1800 or a 2000 milliampere hour battery that's lost some capacity. But the only way to tell is to take it apart. So I'm going to tidy up here, and then the next part of the video we'll destroy this thing, probably permanently. Time for the teardown. So I'll be taking this apart. I will test the cell inside it. It'll be interesting to see what capacity it is and what voltage it's currently got, given the way it slowly ramped the voltage down, making a sort of noise that suggested the boost converter wasn't very happy. So it looks like the only way in is going to be through this bit in the top. So let's try the spudger. The good news is the cell in this is almost certainly discharged, so chances of anything spectacularly unfortunate happening are pretty low. Oh, that looks promising. It's making all the right noises. Oh, there are clips, okay. Gotcha. Okay. So, that does indeed look like an 18650 and a very small circuit board. And that does not look like, I don't know if you can see there, zoom in slowly. Clearly you can see that. The metal contact which the positive wire is affixed to, well, this quality doesn't look great. So the metal contact that the positive wire is affixed to doesn't look like it's terribly securely fastened, which may be part of the reason why the supplied current wasn't very high for more than about 10 minutes. These little wires are also very small, so again, they look a bit bigger in this picture. If I zoom back out again, you can see the sort of scale. Okay, so let's see if we can fish the bits out. This has been taped up with, yeah, it's sticky on the outside. Okay, there's not much information, but everything comes out of the box. Relatively dense little circuit board. So well, that's just a plastic cap, and it is attached to the staked on. Try and keep this in focus. It is attached to the staked on terminal, so that's okay. So this is just a cover for the cell. Nothing obviously capacity related on this. Nothing else. Turn back out a bit. Nothing obviously capacity rated. So the circuit board I suspect is one of the standard little modules. So first things first, let's get the meter on this battery and see what you can make that out good. I'll try and do that without blocking a view of the meter. Let's just do it end to end. So it's currently at 3.1 volts, 3.17 volts, this cell. So it's not as badly discharged as I feared it might be. But it looks like the protection circuitry, either the protection circuitry in this doesn't cut it off as cleanly as it should, or it just runs it down until the boost converter can't get any more out of it. I'm not quite sure which. This is not my area of speciality. I also don't have a magnifying glass, which would probably be helpful in this. Get that in focus. There we go. Wobbling around a bit. So this is the side with the micro USB. Again, it's there's a little DWA1 charging circuit, which anyone who watches Big Clive will be familiar with. It's a surprisingly sophisticated board, this. And there's the side with the regular USB, which appears to only have passive component. That's transistor by the looks of things. 2A, I think, is what it says on that. I don't know, yeah, you can just about make that out. So it's a tiny little board, but it seems to be limited in the power it can deliver. Is there anything being output on the terminals as we speak? Zoom back out. I'm just going to probe the two USB. To refocus, so the two USB port power lines, which you can't see at all probably. Yeah. Yes, there's currently nothing being output on there. I'll plug the Christmas lights in. This may of course just be sufficiently dead at this point that it's not going to do anything. It does seem to be the case. Fine. So I guess the next step could be to charge this up slightly. Move the meter out of the way. This gives me a chance to try something else. Where have it gone? Oh, there it is. I've got another little USB meter, which I've been looking for an excuse to try. Which does show up really nicely on the screen, which is good. So if we plug this in, okay, little charging light has come on, as you can see. So this is currently charging at 0.7 of an amp. 2.3 volts climbing. That's good. We'll get it up to 3.4 and then give this another test with Christmas lights. Shouldn't take too long. So this little meter here does actually show up quite nicely on the screen, which is nice. The other nice thing about it is it's apparently got Bluetooth, which means you can log data from it, but I haven't tried that yet. But it could be interesting. So how are we doing? .38. Nearly there. There we go, 3.4 volts. That'll do. So hopefully that'll be enough to wake it up. Oh, this is warm. So Christmas lights are on. Try that again without the beeping. Right. I'm going to unplug this little meter and go back to using the USB supply as a stand for the meter, because that seems to work a bit better. So, if I can probe across the USB port power lines, which are the two outer ones. Okay, so it's not outputting anything at the moment. So it may be that that's not true. I wonder if it's detecting something being plugged in based on something, probably the grounding of the case. He says he's failing to get a reading anyway. There we go. So 5.2 volts there. So the little blue light does come on. You can see when it's plugged in, so it is clearly detecting that something's plugged in. Whether it does that by relying on... Let's try this again. Apologise for not being able to see this very well. Oh. So there is 5.2 volts across the pins right now. Quite consistently as well. So I do not know if this ever shuts off. I'll tell you what we could do. Let's have a look at how much power it's drawing. Let me just get the... Just going to pause for a second. Okay, I have here a pair of meter leads with crocodile clips on them. So I'm going to attach them. They're a bit big, but So it's not drawing much. So about 14 microamps, which is a standby current, isn't bad actually. Just much less than I expected. So it's not very much at all. So this isn't quite as bad as I thought it might be, which is good news. Well, it's indifferent news really. It's still not a terribly usefully sized power bank. It can't supply enough power to run a modern smartphone, which is the major issue. You try and plug it in, and you get the constant charging, not charging notification, which would fit with the power spikes we were seeing during the power test. So, alright if you've got an old small phone, but less good if you're trying to run anything more modern. But an interesting teardown nonetheless. I have no idea what the actual manufacturer for these is. It appears to be, there's no identifying marks on the little circuit board. Turn the meter off. No identifying marks on the circuit board that I can see. It just appears to be a generic little USB module, but a good first teardown, good first test. I'm just going to have a look and see if I can find out what spec this battery is. 1 second. So I've had a look online for these cells. The ASO seem to be a common manufacturer for cheap 18650s in low-end consumer devices, but they don't publish any information about their what their product codes or model numbers mean, and as far as I can tell there's no consistent identifier in this that identifies its capacity. So we know from the previous test it's somewhere around the 1500 milliamp hour mark, maybe 1800 or 2000 depending on the efficiency of this boost converter, but not particularly high capacity cell. It does have a reasonable weight to it though. Let's continue with that active sabotage and weigh it. You may not be able to make that out. It currently says 0, and the cell weighs 42.6 grams. So, hang on, I'll probably adjust the iPad so you can see that. 42.6 grams. Which is, I mean, it doesn't feel like one of the super cheap, super empty ones, but neither is it massively dense. But so, final conclusion, this thing's not very good. I mean, it nominally works, and it has somewhere over a 1000 milliamp hour capacity at 5 volts, but it's not capable of powering a modern smartphone, and that's kind of what power banks are for. So this one is garbage, but that's fine. It was free. It's 3-4 years old, and I don't know the manufacturer. So a good test run, but hopefully we can test some useful power banks now. Thank you very much. If you like the video, please subscribe, and I'll be doing these regularly. I'll also be doing some videos that explain a little bit more about the testing methodology and how some of the equipment I'm using works, but those are for a separate video. Thank you.